Hello, and welcome to the module Feedback Control. In this module, we're going to be going over our feedback circuit in a little bit more detail. We've already designed the other parts of the circuit, and we know fairly well how our control signals from our feedback circuit are going to generate some DC voltage for our motor, which is going to generate some speed, which we're going to read as an encoder frequency, which is going to loop back around through our speed sensor into some reference variable. But we'd like to take a little bit closer look at exactly how we choose the parameters in our feedback circuit. If you recall, our full circuit's going to look something like this, where we have our motor driver in the middle, and then a speed controller for both sides of our motor, or a feedback controller for both sides. We're going to use control inputs C1 and C2 in order to change directions on our motor, where only one of these will be high at a time, which will enable a single one of our control loops. We have a single speed sensor circuit, and we can use the output from that speed sensor circuit for both of these feedback circuits. Now what we're going to look at today is just a single side of this, so we return to this model where we have one of these inputs grounded to our motor driver. And you can see we have now our enable input for this feedback circuit, as well as our reference voltage input. And we're going to input some reference voltage, and our feedback circuit is going to take care of making sure that the actual speed voltage matches our reference voltage. And that's how we obtain speed control. So our feedback circuit is going to force this node to be the same voltage as this node, meaning that we're going the exact speed that we wanted to based on our reference. When we wrote this system as a block diagram, remember we had separate blocks for the three different parts of the circuit. Our integral feedback controller turned into these two blocks here, a summation and then a gain block, where this is our integral compensator. Our speed sensor became a simple gain block, such that omega simply multiplied by k sense equals Vs, where this k sense was dependent on our T on time that we designed with our 555 speed sensor circuit. And finally, we had a block for the transfer function of the motor and its driver. This transfer function takes a voltage VO and generates some wheel speed omega. Now the transfer function for that motor driver we didn't derive directly, but there are some materials online to show you how to do that. What's important to note is that we can model this motor as a single pole system. So you can see here we have some gain on this transfer function, some G0, also seen down here, where G0 is dependent on our motor parameters. This is that K that we solved for. Then we have some pole frequency, omega M. So that's the pole of our motor, which is also dependent on our motor parameters. Here we have R is an equivalent resistance equal to this. So that's dependent on our motor parameters as well as the BJTs that we've used. Now we can calculate all these constants, G0, omega M, just based on the parameters we derived in the previous labs. And here you can see an example of how that's done. Just plug in the numbers you had and you end up with an answer for G0 and omega M. Now what we'd like to do again is take a look at the overall transfer function of this system. We want to look at the relationship between our reference voltage Vref and our output omega. So in the previous module we looked at how you could do algebra with this block diagram in order to generate an equation relating these two, a single closed-loop transfer function for a full motor driver system. So here we've rewritten out the full closed-loop transfer function for our motor driver system. Again, we have G of S is going to equal omega over Vref. It's the transfer function between these two. And last time we saw that that was 1 over k sense times this loop gain over 1 plus the loop gain. But if we expand that out, we'll get this expression here for G of S. So this equals G of S. Now the way that this transfer function is written is in standard form, and it's standard form for a second order system, which is where we put the denominator in terms of this parameter zeta and omega naught. So we have the natural frequency of this transfer function omega naught, and we have the damping ratio of this transfer function zeta. Now, where exactly the roots of this denominator are is going to depend how our system reacts to inputs. It's going to determine how the transfer function reacts. And so we'd like to see how could we modify what these parameters are in order to get the response that we want from the system. Now if we look at exactly what omega naught and zeta are, if we simply expand these out in terms of the parameters that we know, you can see omega naught depends on a couple of our motor parameters. Again, this is that equivalent resistance we saw up above in the previous slide. It depends on K sense from our speed sensor, and it depends on this K sub I. Now K sub I is our integral controller gain, and we can directly control that by choosing a capacitor and a resistor. But everything else in this equation is fixed. We've already designed our speed sensor, and our motor is just the way our motor is, and we can't do anything about it. Additionally, if we look at zeta, our damping ratio down here, we can see the same thing. We have a couple of motor parameters, our speed sensor parameter, and our integral gain. So what we're going to do is we're going to modify this integral gain K sub I in order to get the desired response from our transfer function. It's really the only knob we can turn in order to change the way the system reacts without changing anything else important about it. So let's take a look at what varying K sub I does. And we're going to look at this in terms of what varying K sub I does to zeta, the damping ratio. So again, here's the transfer function that we're working with, g of s. And let's look at the first type of response. This is an overdamped response. Now what we mean by overdamped is that both of the poles of this denominator are real numbers. What that means is if we looked at them on a pole zero plot, there'd be maybe one there, and there'd be maybe one there. We're going to have two poles along this real axis. Now if zeta is very large, then this first pole here is going to move all the way towards this imaginary axis. It's going to get really close. And you can see what that means in terms of the step response with this plot. Now what this plot looks at is what omega, the output, looks like versus time given a step response in our reference voltage. So we've commanded our motor to go to a new speed, and this is what omega does. You can see for these large zeta values, it's very smooth, but it takes a really, really long time to get to where we want it. And as we start decreasing zeta, it starts going faster and faster to get to where we want it to go. Now we obviously don't want our system to respond like one of these lower curves. It's going to take forever to respond to reference changes, and we're going to be waiting on it all the time, waiting on it to get up to speed or to slow down. So we don't like that. Now let's take a look at a second type of response that we can get from this second order system. Now whereas the previous type of response, the overdamped response, had two real poles, the underdamped response has two imaginary poles. That means we have two complex numbers for the poles of this denominator. If we plot those on our real imaginary plane, that's going to put poles somewhere on this circle we've drawn here. So depending on exactly what the damping ratio is, these poles are going to move back and forth along this circle. They're complex conjugates of each other, so they're always going to have the same real part, but their imaginary parts will be the negative of each other. Now, if these poles are placed really close to the imaginary axis, if they're almost all imaginary, we're going to ring quite a bit in our system. We're going to get a response like this. And in fact, if you're close enough to this axis with these poles, your system is simply going to ring forever, and it's going to be fairly unstable. You can imagine that's not what we want to do with our motor. We'd like to give it a reference voltage and have it go to that speed without just ringing around our desired state forever. As we start to move these poles down, as we start to increase the real part of them and move them closer to the axis, the real axis, and further away from this imaginary one, we can start to reduce the magnitude of this ringing and have our system settle to its desired reference value faster and faster. Now eventually, if we move these poles back far enough, they're going to hit the real axis. And let's take a look at what happens when we're there. Now in this case, with a critically damped system, we now have a double root for this polynomial down here. So we have two poles, but they're at the same location. What that means is that they're both right on top of each other right here. That gives us a response, as you can see at zeta equals 1, of something like this. Now notice that we're both reacting fast enough to our control inputs. It's not like these over-damped cases. And we're not ringing. It's not like these under-damped cases. And so we call this case critically damped. Critically damped is when we have a double pole for the denominator in the second-order system. And that's what we'd like to solve for. We'd like to adjust our integral gain k sub I such that we have a critically damped system. Remember, adjusting k sub I is going to vary zeta and is going to allow us to change how our system reacts. We want to solve for k sub I such that we have a double root. We'd like to solve for this so it has a double root. Now we can do this by hand, or we can do it using some program, Mathematica or something, but that's fairly difficult, and for larger systems it's just going to become unwieldy. It's not going to be an easy thing to do. So let's take a look at how we might do this using the built-in MATLAB tools in order to design a feedback circuit like this. Now MATLAB has a tool called SISO tool. That's S-I-S-O tool. And that stands for Single Input, Single Output tool. And it's made for designing single input, single output systems. Well, if you recall what our system looks like, it has a single input, this vref, and a single output omega, so it should work fairly well. Now what SISO tool does is it assumes some sort of topology, and this is one of the topologies it assumes, and you can see that it's very similar to our system. And you can simply plug in your parameters, so we'd plug this in for G in SISO tool, this in for H, and then plug in your integral controller k sub I over S for C. And SISO tool will allow you to modify k sub I and to see how the closed loop response changes as you modify it. And so you can simply slide the gain around, see how the step response changes, and design a system with the output characteristics that you want. So that's one of the better, more intuitive ways to design a system like this, and it's what we recommend you do for your system. We've provided a script online. It's called systemtfsetup.m. So just save that into some folder, edit the values to make sure they're the same ones that you used with your motor, and then type SISO tool and import your parameters. If you want to, you can additionally simply solve for what k sub I gives you zeta equal to 1 using the equation for zeta on previous slides. You can do that and compare what k sub i's you get from each of these two systems. They should be about the same. In any case, once you've solved for k sub I using SISO tool or the equation to determine what it should be, you can simply find a set of resistor and capacitor to use on that op-amp feedback circuit in order to give you the k sub I that you wanted. And once you've done that, you should have a fully operational feedback circuit. You should be able to give it a speed reference, and that should go into whichever feedback circuit is enabled. Remember, only one of these is enabled at a time. And you should arrive at the desired speed that you wanted as fast as possible, but without any ringing on the system. That's what solving for a critically damped system with zeta equals 1 will do for you. Now in your demo, we'd like you to hook up a waveform generator where this V reference is, and then you can give that a step, or you can just vary it and show us on this sense PWM, the output of your speed sensor, that your motor is in fact tracking the speed that you set with VREF, and that it's getting there in a timely manner, that it's not taking forever, that you don't have an overdamped system. Also, that it's not ringing too much, that the sense PWM frequency is fairly constant. It shouldn't be ringing back and forth around the set point. And that completes our speed control circuit. Once you've solved for the parameters that go into this feedback circuit, we've already built this and we've tested it. Our speed sensor, that was a long time ago, we did that. And now we have a system where we can give a reference voltage as a PWM signal if needed, and tell it which direction to go. And at this point, in the next lab and the ones after that, you'll be able to hook up a microcontroller right here, let a microcontroller control these inputs, and tell your robot to drive around however you want it.